Welcome to my final presentation for EduTech CS6460. My project is on detecting AI-written essays, and my name is Benjamin Ostrauer. So to start off, the motivation, why is this important? Well, with the advent of ChatGPT and the like, students now have the ability to create very realistic sounding essays. These tools are so sophisticated that ChatGPT was actually able to pass an MBA exam from Wharton. So these tools are very powerful and very capable of helping students out with their academic workload. This problem has weighed on the minds of administrators quite heavily. The Daily Mail is able to report that many municipalities have already banned ChatGPT. LA, Seattle Public Schools, New York. They cite that there's no good ways to detect large language model output, and they believe that half of the school and college students are already using ChatGPT to cheat. These large language models effectively challenge the future of higher education because of this. It makes it challenging to enforce the effects of this plagiarism. For example, how do colleges and institutions combat this? Do they go back to pen and paper? Do they record students at home while they write essays? Do they just do away with essays altogether? It's very challenging, and it's almost impossible for administrations to make the correct decision, especially if they don't have the ability to detect whether students are using this tool or not. So that brings me to the prior work around this topic. And the prior work has centered around several different approaches. The foremost being analyzing the text on a token level. So Glitter and Detect GPT are two approaches that have worked like this. They measure the entropy and statistical likelihood of token choices. And what this means is, to give an example, so if I were to say, the man walks to the blank, there are several choices that could work there: the door, the store, the couch, blank, blank, blank. What these approaches do is they measure they look at the output that a large language model give for that sentence. So, like the model might give store, couch, door, etc. And then they compare that output to the actual word choice given in the sentence. And then they run hypothesis tests and statistical tests on the likelihood that a document might use, 10 words outside of the top 10,000 large language model choices. Another measure is coherence measures. So Zhang, in his neural deepfake detection of text paper, created a two-pronged approach to detecting fake news by using an architecture that combines factual coherence and next sentence prediction. Factual coherence, in this sense, he had a really neat way of doing it. What he did is he would parse out all the pronouns in a document using named entity recognition. And once he had that, he would then embed these pronouns into a low space dimension using a embedding choice called Wikipedia 2vec, which allowed him to basically use the knowledge of Wikipedia to assign categories that a topic would belong to. So take, for instance, a essay was written on, started writing about McDonald's and Burger King in the first half, and then switched to Jupiter and Saturn in the second half. The named entity recognition would be able to pick out all four of those pronouns, and then the Wikipedia 2vec would be able to cluster the McDonald's and Burger King and restaurant fast food burgers, and the Saturn and Jupiter into astronomy and space and stuff like that. And then he could obviously use distance measures to kind of create proxies for factual coherence. And then the other side is next sentence prediction. This works very similar to the analyzing the text on a token level, but this time on a sentence level. What happens is you use a transformer network like BERT to pass a sentence in, BERT creates a sentence after that. You then compare that created sentence to the actual sentence, and then again use similarity metrics to see how similar those two sentences are. The next approach is abstractive summaries. So Esmezalda, in his neural abstractive text summarization, created a pointer generator network to create abstractive summaries of news articles. And the byproduct of this is that he used these as inputs into a simple long short-term memory network to detect whether a news article was written by a machine or not. And then finally we have automated essay scoring. So this isn't necessarily detecting AI text, but the methodology can be co-opted to do that. Ludwig, in his automated essay scoring, used transformer models. He would create embeddings of the essay, pass it through a transformer, and it would output a score. So my methodology is to combine all these approaches into a single unifying approach. I crafted a neural network to encompass all these into a binary classification model and then compare this against a baseline method, in my case a long short-term memory network with a convolutional neural network. I created diagrams at the bottom here. The left one is my network. You can see the essay and the summaries get passed through a BERT architecture because they are text, and they are concatenated along with the token counts, the next sentence prediction logits. These are then passed into a multi-layer perceptron feed-forward network, and at the very end it's squashed with a sigmoid activation function where the output is put between 0 and 1 for our classes. The long short-term memory network and the convolutional neural network is similar, except it's just only using the essay, and it's passed through two convolution blocks, a long short-term memory network, and then again a sigmoid activation function to squish the predictions between 0 and 1. So some highlights from my project. Number one, I scraped 20,000 essays from EduBirdie, which is a online website to write essays for students. They have several thousand, tens of thousands of free ones. Due to computational constraints with some of the other parts of this project, I had to whittle this down to 1,300, which basically amounted to all the essays with 500 words or less. I then created AI-written essay equivalents by feeding in the title and essay word length to a prompt using the Falcon 7 billion parameter instruct large language model. The prompt I used LangChain for the interface, and I would pass the prompt, "You are a student, please write a blank word essay on blank," feeding in the essay word length rounded to the nearest hundredth and the title of the essay. So I ended up with 1,300 real essays and then 1,300 fake essays. I then calculated the number of top 10 samples words for both human-written and AI-written text. To do this, I would start with the 30th word onward to create some context behind the meaning of the words. And then every fifth word, I would then pass in the preceding sequence into a large language model, have it output the next word for it, and then compare that to the actual word. So for example, for the first 30 words, I would take the 29, pass it into the model, it would spit out a new word. I would compare that 30th word, that new word, to the 30th word in the essay, and then if it was in one of the top 10 words produced by the large language model, I would increment and then go through the essay every 5 words, counting up the number of words in those top 10 lists. For the next two, I used the Hugging Face transformer modules. With the extractive summaries, I used Google's T5 conditional text generation to create both summaries for the human and machine-written essays, and I would also use the BERT's next sentence prediction module to basically, as I described earlier, pass a sentence in, it would then create a sentence, and I would then go look at the next sentence in the essay and compare that with the sentence produced by BERT to see the similarity score. So interesting finds. Number one, the inference for the text generation models, even on smaller models, 7 billion parameters is actually considered small. ChatGPT-4, I think, has a trillion some odd parameters, so relatively very small. It's still very expensive to run those text generation models. Comparatively, the inference for the masked input is actually much lighter. You could run that on base Google Colab version, whereas the former required Google Colab Pro Plus. To the right here, I have the count of top 10 tokens in a given essay. So these are just box plots that show you the average, the quartile ranges, and some outliers. As you can see, the AI kind of has a larger range of values to take, but the average of both of them are very similar. For the next sentence prediction, basically what happened is I had 28,000 human sentences from human written essays. I would take an essay, split it by punctuation, and then that would give me the sentences that I would pass in through. Of the 28,000, only about 1,000 had a similarity score lower than 50%. 3,200 had similarity scores below 99%. So very, very small percentage of these sentences had lower than 99% similarity scores. And with the AI written essays, I only had 18,000 comparatively sentences to analyze. Only about 100 had a probability lower than 50%, and only 400 had similarity scores below 99%. So, as you can see to the right, obviously most of these had similarity scores of 99% or above. For the human next sentence prediction, though the outliers, the 3,200 that weren't 99%, they're very evenly spread out from 0 to 99. Whereas for the machine, it's kind of clustered around 90% and then again below 30%. It's very sparse in between that inner 50 percentile range. And then finally, looking at the summary counts, the summaries of AI written text were slightly longer than those of humans, although extremely similar, 44.2 words to 44.16. The AI written texts do have slightly less spread in the length of the summary. The average standard deviation was 9.36 to 9.29 for an AI written text. However, interestingly enough, the human written essay summaries have more unique words than the AI ones, almost a full word on average different. So finally, this brings us to the results. Unfortunately, the models did not perform very well. The likely culprits are the architecture and dataset size. So running these models are very, very expensive. I had to use Google Colab Pro Plus, and you only get so many compute units a month. And for the Transformer and MLP network, the one that I created, I only ran it for 5 epochs. I ran them both for 5 epochs for standardization, but the Transformer MLP network only ran for 5 epochs because it was very expensive to keep that running, and to iterate through a lot of different architecture changes is very difficult. So in future work, being able to run that for larger epoch could absolutely help the model. Another factor is dataset size. The fact that I only have 2,600 essays as opposed to the 20,000, really the 40,000 that I wanted to have, is a stark difference. I mean, 2,600 essays isn't really that much when it comes to neural networks. You really need a lot of data. And finally, some good news is that the Transformer MLP network did slightly outperform a baseline of the CNN LSTM. And finally, on the last slide here, I have the confusion matrix for both, just to show you the performance. So basically, to train these models, I would split 80% of the model into the training data set, where the model would learn to associate the features with the output. And then I would set aside the final 20% of the data set as a test holdout to try and see the performance on unseen data for both models. And on the left here, we have the labels 0 and 1. 0 being that it is not the 0 is a human essay, 1 is a machine-written essay. So on the left is the true label, and the bottom is the predicted label. So in the top left corner, that's a true label of human and a predicted label of human. And the bottom right is a predicted label of human and a real label, or a predicted label of machine and a real label of machine. So as you can see, the Transformer network was very heavily predicting human written essays. It got a lot of them wrong, about half, but it was able to actually predict some machine-written essays correctly, whereas the LSTM-CNN network only predicted machine-written essays. And again, you know, a lot of this is due to the fact that the data set is small, the architecture wasn't complex enough to, sort of keep this shallow. The LSTM-CNN needs to be a lot deeper. It needs to run for more epochs. So in future work, that could definitely be something to add on to here, because these results could be better with more computational resources and time. So thank you for listening to my project, the end.